Swayamprabha. Digital India. Educated India.
Yes, we will take some questions and answers today. We will try to build a set of frequently occurring questions in people's minds.
We have been discussing about various spray nozzle designs. What is that, evaluating, for performance evaluation, what is that we have given a different set of nozzles? How do we evaluate its performance, maybe in terms of efficiency or anything else?
Very important and very industrially relevant question. So, I will write down the question and then we will go through a process of answering it. What is the process of selecting an appropriate nozzle for a given application? This is obviously a very important question. Now, I want to emphasize one thing. I want to first emphasize this keyword selecting. So, we are not going to talk about how a nozzle is to be designed. There are, let us say, 100 or a few thousand nozzles that are available. We are going to look at how to select the appropriate nozzle. Now, the constraints that are posed by the user. So, let us talk about those first. So, if you are the one that have been given the task of selecting an appropriate nozzle, these are questions that you have to ask your customer. So, let us say some Procter and Gamble comes to you and says, help me select a nozzle. These are the questions that you have to ask the company that has come to you asking for help. Okay. So, first question, what fluid do you want to spray? And subsidiaries to this are the physical properties that are relevant, which are in the terms of viscosity, surface tension, density of the fluid, etc. Second, what spray angle do you need? Now, why is this a customer imposed constraint and why is it not a variable that is available to you? Very often, let us say I will answer this in a slightly, very often there is an existing installation. Let us say this is like a spray dryer. Okay, and the spray dryer has a bank of these nozzles at the head, each one putting out a spray of sorts. If I make these too wide, then the issue of impingement on the walls, etc., becomes relevant. So, let us say I have a fan here that is driving an air stream. So, I am putting out hot air here. and this air has to essentially reach out to all the drops. So, which means it cannot be too narrow, and the constraint that comes from the customer is in terms of, let us say, what size kiln do you have, and depending on the proximity of the last nozzle to the kiln wall, you want to design the cone angle appropriately, you want to choose the cone angle appropriately, and therefore, you need to know something about the installation design in order to answer the question of what spray angle do you need. Next, what spray pattern, what supply pressure we will come to the spray pattern later, what supply pressure do you have available? Okay, so that is going to determine something about the spray nozzle itself. What flow rate per nozzle do you need? Now, this is usually determined from throughput. So, again, if I was a powdered product manufacturer, there is a certain throughput that I need per nozzle or per kiln. So, I need this kiln to produce let us say so many thousands of pounds of a product per day. So, those kinds of numbers can be translated to flow rate per nozzle. So, and then lastly, do you have other sources of atomizing energy? Possible choices are, let us say, air or steam at some high pressure, let us say. There is one last question which your customer may believe is just simply Greek and Latin, but what drop size do you need? Very often we find in the industry that drop size is something that they really have no control over. I mean, they really do not try to control. So, it is like it is an afterthought, okay, but it is worth asking the question, especially like I said with the product manufacturer example. Okay, so, let us go through these questions and see how the design or selection process is influenced by each of these. So, if you go to so the first thing, once you gather this information, the first question that is of importance is number 5. Okay, the first question that you should use in the selection process is number 5. If the answer to that is no, that there are no other sources of atomizing energy, then it is pretty clear the choice has to be a pressure swirl atomizer of some kind. Okay. If they do have, let us say, air or steam available, then you can go to an air assist or an air blast atomizer, or steam assist, steam blast. It really does not mean it is the same thing, some kind of a gas assisted atomization. And so, essentially the first, so I will write down the steps that you can go through. In the selection process. First, then you are restricted to simplex nozzles as pretty much the only choice. Now, if they, so we will go through this one by one. Let us say we want to look at simplex nozzles. How do we choose simplex nozzles? Take the flow rate that you have, okay, and we will call this some q dot. You can calculate a number called the flow number. This flow number in very crude terms is defined as q dot over square root of delta p. Delta p is your supply pressure choice, q dot is the volume flow rate. So, this q dot over square root of delta p obviously is not a non-dimensional number, as you can see. So, you have to calculate this in a set of units that a particular manufacturer's catalog allows. Like for example, there is several manufacturers of simplex nozzles in the world. I will list a few. One is called Spraying Systems. There is another company that is called Delavan, and then Parker, and then another one called Hago. There are ones called Danfoss. These are all, you can go find information about, you can get catalogs of each of these manufacturers, and each of these manufacturers would report this flow number in their choice of units. Let us say for example, meter cube per second per kilopascal would be one choice, or gallons per hour per psi or square root of psi. Okay, gallons per hour per square root of psi is a perfectly legitimate unit for flow number. So, you can calculate this flow number, and typically you have a selection of nozzles that give you the same flow number, but different flow rates. Okay. So, the first step is calculate flow number, but before you can go to the catalog, what you need is a scale the flow number with viscosity, okay, with liquid viscosity. So, in other words, most of these catalogs would have the flow number or all the flow data on all the nozzles reported with, let us say, water or kerosene, depending on their main market segment. Now, if you are spraying a fluid that is different from the test fluid that they are reporting the data on, you need to figure out a way to scale your flow number calculation to what the flow number would be equivalent to their catalog. So, typically this flow number 1 divided by flow number catalog is some mu 1 divided by mu catalog raised to the power alpha. Now, the alpha itself would be a function of the design of the spray nozzle, and most manufacturers give this number alpha. Okay. So, I know my flow number Fn1, I know mu 1, the flow number of the viscosity of the fluid that I need to spray, and I know the flow number, I want to know the flow number in the catalog. I know mu of the fluid that they use to test their spray nozzles, which is mu catalog. So, mu 1 is viscosity of my fluid, mu catalog is the viscosity of the test fluid. So, from here I can get what flow number in the catalog would give me the would be equivalent to the one that I want to spray. Now, here is a bit of a surprising fact, but true, that for a given mu, as mu increases, the flow rate through the same nozzle at the same pressure increases. Okay, especially true for simplex nozzles that we looked at, and it has to do with the fact, it is a little surprising because you expect viscosity goes up, you expect the flow rate to come down, but the flow rate through these simplex nozzles goes up, because if you remember the design of a simplex nozzle, you have a swirling liquid that is exiting the nozzle in the form of a film that is sticking to the walls. As the viscosity goes up, that swirl intensity dies out much quicker inside the nozzle, as a result of which the film exiting is actually thicker. So, even though the axial velocity remaining, the film is thicker, the axial velocity remaining the same, you get a slightly higher flow rate. So, this number alpha is on the order of about 0.1 to 0.2 typically. So, it is a positive number, it is not a negative scaling with mu. For the same delta P, if the viscosity goes up, the flow rate goes up slightly. Again, just to make sure we have this point under wraps, the thickness of the film covers only about less than 10% of the total cross sectional area. So, we are only talking of a small increase in that thickness, going from let us say 10% of the cross sectional area up to 15% of the cross sectional area to give us a weak exponent like 0.1. So, the exponent is only like 0.1. So, it is like it is very insensitive to viscosity, if any slightly it increases slightly. So, this increase, slight increase is well captured by just that small increase in the film thickness at the exit of the nozzle. Okay. So, the process starts by calculating the flow number in the same units as the chosen catalog. Now, if you really want to go through this, let us say you have 5 different manufacturers catalogs at your disposal, each one has their own unit system, you will have to get the flow number in those various units. Now, alpha specifically depends on the design. So, if the catalog already does not have it, you can call the manufacturer and they are usually happy to give you this number, but if you are at loss, a number like 0.15 is reasonably accurate. Okay. So, you can now get the flow number for the catalog for your actual nozzle. Now, this is sufficient to get started. So, the first question to go after is 5. Once you have that, use the answers to question number 4 and 3. So, we are starting with 5, we have gone to 4 and 3, and then we come to 2. So, in this step number 2, we have used question 4 and question 3. Once you know your flow number, we will use question 2. Now, at this stage, most of these spray nozzle manufacturers have what is called a spray pattern designation. in terms of what are called solid cone spray nozzles or hollow cone spray nozzles or mixed spray nozzles, sort of like a small, medium, large. Okay. So, essentially a solid cone spray nozzle would be where if I took a disc, the entire disc has drops in the cross section. This is an example of a solid cone. If I did this on a hollow cone spray nozzle, I am expecting there would be like a donut shape. Okay, so, the size of the donut varies between hollow cone and the mixed version, but essentially these are two variants of the spray pattern. So, for a given spray angle, and a given flow number, you may have 2 or 3 choices. So, the best way to go about this is one. So, the way to select pattern use engineering calculations for the specific system on hand, or what is the second option? One, use some sort of engineering calculations to make sure you are able to get enough penetration of the air into the spray, or if it is a combustion application, try and see how the combustion would be shaped by a given kind of a spray. Or the second option is to simply go through trial and error process. So, you try out all the 3 or 4 different nozzles, you basically whittle down from a catalog of a few thousand nozzles down to about 3 or 4. So, your best bet may just be to try out all 3 or 4 and see which one gives you the best performance. But if the trial process is expensive, like maybe in some cases, you may need to go through some calculations to really come down to one nozzle as your specification. So, this is if the answer to the first question, if the answer to Q5 is no. We will write down the exact same process if the answer to question 5 is yes. Okay. So, essentially if you looked at the previous design process, we did not really get down to drop size in any way, because if I specify cone angle and flow rate, there is a good chance that cone angle and flow number, I really have lost all the controls over the drop size. I really do not have any other handles to control drop size at that level. Whereas, with air assist atomizers, I have another independent control over drop size. Okay. So, this is where one would need some more information about drop sizes. But the first step before you get to drop size, so I will show you how we usually incorporate drop size into the design process, or at least the selection process. But before that, what we want to do is look at how we are going to use the air. So, there are 3 or 4 possibilities. One is an internal mix air assist design, or an external mix air assist design? Now, the answer, so this is a question that we have to ask ourselves. After we know we have air available, do we go down the route of selecting an internal mix design, or do we go down the route of selecting an external mix air assist design? The answer to this is usually based on some other considerations like safety. Like for example, in a combustion system, it is highly unlikely to be an internal mix design, because you do not want to mix your fuel vapor and oxidizer in any way or form prior to combustion. It is just not safe, especially because the nozzle itself is going to be subjected to a high temperature environment. Okay. If you are in a spray dryer kind of a situation, it could be possible, but generally speaking, most commercially available spray nozzles are all external mix design. I should not say all, there are internal mix designs available commercially, but they are prone to instabilities. We will talk about those when we look at regime maps later on in the semester, but essentially if I want a very robust installation, I would choose the external mix air assist design. The disadvantage with that is that they are not as efficient with the usage of air, with the air usage as the internal mix designs, but they are less prone to instabilities. So, I will sacrifice some efficiency for a nice robust installation. So, typically we go with an external mix air assist design, and in these external mix we looked at 3 or 4 designs in the earlier lectures. There is a process exactly like this. You start, because all of the external mix designs are essentially like a simplex nozzle with an outer air sheath. So, I have a simplex core that I am using air outside. So, the selection process associated with selecting an air assist design starts with selecting the appropriate simplex core in the form of the flow number, in the form of a cone angle, etc., and then you can use the similar calculation on the air side to choose the based on the spray cone angle that you want, to choose the equivalent air assist design. So, this process essentially begins just like we said, air assist design. Now, once you have narrowed down on the external mix air assist design, the design catalog or selection catalog usually gives you a flow number for the air side. Okay, so, what flow rate of air? Square root of delta P across the air passage. Because this is an external mix, the air passage is like a separate fluid dynamic passage in relation to the fuel side. So, I can calculate an air number, a flow number for the air side as well as a flow number for the fuel side, and typically using these two numbers you can choose an air assist design model. Now, drop size, because you have this additional handle of the air assist in the air assist atomizer, you can go to what are called the Sauter mean diameter correlations. So, typically the Sauter mean diameter divided by, let us say, the diameter of the orifice would be in some form, would be given to you in the form of a correlation like this, based on the Weber number and the Ohn-Zorge number. Okay, we will write down what these are. The Weber number is defined as rho u relative squared d0 over sigma, rho being the air density, u relative being the relative velocity between the liquid film coming out and the air stream outside. D0 could be like the diameter of the orifice through which the liquid film is coming out, and sigma is the surface tension of the liquid. Ohn-Zorge number I believe is that. Another way of thinking of this is essentially square root of the Weber number divided by the Reynolds number. Okay, this is an easier way to remember this. Okay, the Reynolds number also is defined based on rho u relative d 0 divided by mu. So, I can use a correlation like this to figure out what air velocity do I need, because I have fixed the flow number on the simplex side. So, I can, the u relative is the liquid film velocity minus the air film velocity, or actually that is the other way around, air is usually moving faster than the liquid, right. So, I need to know, I can from a correlation like this, given an SMD that is desirable, I can find W e, the Weber number for that given application, and from there calculate what U air would be best, would give me that Weber number. So, here is a way to engineer a spray nozzle for a given drop size. Okay, I am only able to do this because I have this additional handle, we have to realize that. And that too only a mean drop size. If I want to engineer a drop size distribution, then it is no longer a selection process, it is a design altogether.